graphics and math and stuff.
Good evening. How's everybody?
Good.
Good. How's your week going?
It's the first week.
So for you who has read the syllabus, what do you think? 3 pages. You didn't read it, did you? Any question on the syllabus?
So we don't view the book, is that correct?
You don't need to.
I can find it myself.
I can recommend some books for reference, but we don't really use the book for anything, really. But you haven't bought the book, right? It's good for reference, but it's a different architecture. Did you buy it new?
No.
So any question on the syllabus? What about last lecture? You guys check the website? Good? Everything's there? Makes sense? Any comments, critiques?
I was just curious about the labs. Are we all in the same lab, or are we split up? Or?
I only see one section for the lab, so I'm assuming that everybody will be in the same room. I forgot what the room number is. I think it's 2315? 2315, is that the right?
So that's was a Thursday night, right?
Yes, tomorrow night. So let's start. What did we talk about last time? Check course website. Please check at least once a week. If there's anything really urgent, I will email class-wide. But otherwise, at least check the website once a week, please. Attend classes. Yeah. Any question on these topics so far? So the first week, the first lecture, we just talk about the big picture. All right, so please keep these topics in mind, because we will go into a lot more details, right? But sometimes when you go into details, you forget why you're learning the details. There's so many things that pertain to programs, instructions, programming, but don't lose sight of why you're programming. What is a program? Just data. Data is such a loaded word, right? What is data? It's hard to define. But we work with data all the time, especially with computers. And we have to be sure that we understand how computers work with data. So tonight, we'll talk about how computers see data. Right? To know your enemy, you must become your enemy. And what is your enemy?
The computer?
Yeah, enemy is digital, right? So we have to understand how digital systems work, at least in a certain level, right? So modern computers are digital. So we have to be like them. We have to understand how they think to be able to interface and use them effectively, right? Not saying they're enemies, yeah, but why are computers digital? Transistors. We brought up transistors last time. So what's so special about transistors that we have to go digital?
2 states.
2 states, off and on. And guess what? With transistors, we can switch between these states really, really quickly. So if we somehow have a discipline or a set of concepts that we can actually exploit this to make fast computing machines, which in fact we do, because we have your tablets, your phone, pen and paper, computers. Pen and paper is good. So we did it, right? But how did we do it? How did we use these billions and billions of transistors to design and create a very fast computing machine? So, but first, we have to talk about digital. So why digital? Any guesses? Why just off and on? How do you sense things? For example, how do you sense temperature? In what ways can you describe a temperature to me, for example? How's the temperature in this room? On. No, how do you do it? In a digital way or in an analog way? Oh, it's kind of hot, right? Oh, it's about 70s. You don't just say off or cold or hot. There's some gradient, right? Intuitively, we think that way. In everything. How heavy is that desk? Kind of heavy, right? It's not just impossible. Possible. It would be a weird, weird life if you think that way, right? So why do computers don't do this? Why not? You know voltages, right? Why not represent something in between instead of just off and on?
Programs would be really long.
Not necessarily. It could be pretty simple when you can actually represent that it's that
Information will be accurate.
Because two people's definitions are different.
two good answers, right? So in digital, it's really easy to figure out what you mean, right? You see here, so here, in digital, you have a lot of margin to figure out whether you are saying 0 or you're saying 1. Does that make sense? It's easier to generate this kind of signal. Whereas in analog, let's say if you split the signal to 5 distinct values, it's harder to generate this value, and it's even harder to detect these values. It's much simpler when you have transistors to generate this kind of signal. Does that make sense? So with analog signals, it's harder to generate and differentiate. Much more complex circuitry. Much more complex circuitry. I'm not understanding that. It's actually will be more complex. Keep in mind, we did use analog computers to integrate and whatever to calculate trajectory of a ballistic missile. We did have analog computers. Now, you can just have an undergrad, go to MATLAB and start typing in equations. And then digital computers behind it start taking over. Right? It used to be we have real analog computers with discrete components that actually work with voltages. Big pain. Because when you have to change the function, what do? Right? That's why computers are neat, because you just grab a keyboard, plug it in, start typing. Right? And it will be hard to make the signal more robust. So you'll be saying, okay, we are saying that with digital, it's easier to generate just 2 levels of signal. And you have a lot of margin for error. But in a specific time sampling, would you have more information if you go analog?
Infinite amount of information.
Infinite amount. To what cost, though? Lots. Like, if you want to make a more sensitive instrument, either it'll be more expensive to actually amplify the signal, or you have a voltage from 0 to 200 volts for communications. Is that viable? Probably not. Right? But with digital, even though at a certain point when you sample the signal, you can only say it's 0, 1, or somewhere in between, which is error, but you can do that very, very quickly. Do you still see parallel ports nowadays? Ever wonder why? Parallel ports can carry more signal at a time, right? You agree? Serial port only has, what? TX-RX, it's duplex, for example. Parallel port can have 16 wires. You can have 16 bits going on at the same time. But why don't we keep on? Why don't we stick with parallel ports? Turns out when you switch it really quickly, parallel ports getting messy, right? Because you're starting to get crosstalk and everything. But serial, it's easier to make faster buses. That's why you have USBs and everything. Cool. Now, what is the implication of going this way? So now we know that computers work digitally. We have to represent data in digital form somehow. What's data? Just revisit that concept. Can anybody tell me what data is?
Information.
What?
Bits of information.
Information. Right? How can data be represented? Can you be more general? What kind of data is around you? Like, what kind of data do you use? Time. How do you represent time? Is time data? Could be. How do you represent time?
Numerically.
Numerically, 3 numbers or more, right? Hours, minutes, seconds. Make sense? So numbers are a very common example of data. We work with numbers a lot. Just look around you, everything is in numbers. Your shirt size, how to measure things, your clock, your watch, dimensions of things, right? Your computers, everything. The way you list things are in numbers. So numbers come out a lot. So that's why computers have dedicated functions just to deal with numbers, to compute. Make sense? Because we deal with numbers a lot. So a bit, this is the first time you'll see this definition, is the smallest piece of data that can be represented digitally. You agree? So what's the smallest bit of data you can represent in digital? 0, 1. This is useless. Let's say you want to encode temperature. Okay, the temperature right now is 98, for example, Fahrenheit. But I only have 2 possible data values. So how do you do this? Right? The thing with digital, it works with Boolean algebra. We kind of talked about this last time. So what's Boolean algebra?
True, false.
True, false, logical operations, right? So Boolean algebra has existed for a long time, since 18th century, by Michael Boole, or I forgot what his first name is, Boole, Mr. Boole.
George, I think.
I bet. I think it is George. I think I have it in the slide. So we have Boolean algebra since 18th century. Think about it. We have all this math sitting around for centuries, and then we design vacuum tubes, transistors. Now smart people start thinking, hey, turns out with transistors we can make electronic circuits that resolves Boolean equations really, really quickly. And then the gears start turning collectively, us as humans. Wait a second. If we can do Boolean algebra really quickly, we can do arithmetic with Boolean algebra pretty easily. What's next? Pornography. Good. The foremost driving force of technology. Entertainment, gaming, pornography. It's crazy. So, progress, whatever, right? You can count the progress, depending on you. So, with Boolean algebra, things like computing becomes very, very fast. You just jump-started the progress of humans in terms of technology, like exponentially. Since the 60s, 70s, we've discovered so many things. We've seen the deepest stars. We've done a lot of things because of computers. We went to the moon with a computer that right now can be like this small, tip of my thumb. Like chips this small now can power a spaceship that took us to the moon. That's crazy. Like if you, I saw that documentary Moon Machines, like how they actually did different things in the Apple program. It's insane. If you look at a computer, after taking this class, if you learn things, and then look at the computer that you used back in the late 60s, you'll be amazed. We went to the moon with this. The point I'm trying to get across is, we went to the moon with that, right? Now with the power that we have right now in computing, we have many good things. I was expecting you to actually, oh, you missed it, sorry. So our CPU, George, need to start making achievement for this class. So, implications for going digital and Boolean algebra and everything. How to represent data that the computer can understand. Right? So data is represented as a combination of ones and zeros. Give me a wild guess how you represent numbers as a combination of zeros and ones.
Binary.
Binary. We throw that word a lot. What's binary?
Base 2 numbers.
Base 2 numbers. What's a base 2 number? What does it mean to be a base 2 number? What's a base?
Counting base, number base. Number of digits,
Number of digits.
including 0.
Yes. Right? So the answer is, it depends. It doesn't have to be binary. Right? But it depends on it, but we use binary because for reasons we'll see later. Now, so my second question here. Do you ever wonder why programming languages have different data types? Why care? Why can't you use long for everything? Size constraints. So why?
Memory wasn't always as big as it is now.
It takes more memory to store that number.
Are we going to change things now that memory is cheap and everywhere?
Should we?
8 gig of RAM on a cheap computer now? I mean,
Should we?
is it possible?
Already so much poorly. People are already being lazy with their programming.
Oh yeah, very, very lazy. And now that processors are, the increasing performance of processors are not that, like it's not increasing as it used to. And so we're starting to hit this plateau for single core performance. So they're going low power and everything and trying to be smart about other things. But now we're starting to see software that is power conscious and starting to get. So it's interesting to see this trend. Like we've been so caught up with CPU getting stronger and stronger every year. Now that it's tapering off, we have to slow down, back up a bit. Go. So what makes base numbers work with computers is that the fact that we know about positional notation, number base or radix, right? So what's radix? You've answered it. So you took 2 minutes off my lecture time, but I'll do that anyway. I always like to Google things and see what it thinks about what we think we know. Let's see what Google thinks about radix. Google? What?
I said, you didn't name this last week. Good job, Google.
Probably not. Radix,
Better chance to get the name.
the base of a system of numeration. That's not really helpful. A source or origin of something. Judaism is the radix of Christianity. Okay. Did not expect that. Wikipedia. This is more helpful. The number of unique digits, including 0, that the positional numeral system uses to represent numbers. Why is this fact important to us? Any guesses? Why is it important to have positional number system? What is a positional number system? Can somebody tell me what a positional number system is?
Really, aren't they all just ways of translating a common base 10 system?
Why?
That's what we know and understand.
Yes, exactly. Not just we know. We inherently just use. We don't think about it. It's second nature, right? For example, let's do this interesting exercise. So number of unique digits. So for example, base 10, you have 10 unique digits, 0 to 9, with inherent values. The positional number system means what? Each position of the digit implies what? It's
Multiplier in.
yeah, magnitude, right? So, for example, for this number, basically the quantity, the inherent value of that number is 4 hundreds, 7 tens, and 8 ones. Everybody's cool with this? This is important. Base number, good. The thing is, we think of value or quantity in decimal here because what? We have 10 fingers, right? If we happen to have 8 fingers or 16, it would make it easier for us to actually convert between binary and whatever because our brain will be wired for that, right? But with 10, there's some complication trying to convert between the two because it's not powers of 2. Now, tell me, that's a base 8 number. Which value is greater? Which number is actually greater or lesser? No idea. So hard to actually mentally trying to think which number is greater because your brain is so hardwired from base 10, it's just imploding right now.
Base 10.
Somebody trying to write it out. No. Do some mental gymnastics. Can you see it's impossible, right? It's so inherent to you, like that base 10, that you don't know. It's like, what the heck is going on? Why are we talking about this? This is wrong. Computers are stupid. Right? Don't you wish now you have 8 fingers or 16? But you do know how to convert to decimal, right? We're smarter than that. We have evolved like neocortex for millions of years, so we can actually figure out what the actual value is. It's the same value. So this is what I'm trying to make sure that you understand. This is just a representation. The inherent value could be represented by anything, any base, a symbol, a picture, whatever. The only reason we do this is because it's easier to work with binary because our computer is digital. Does it make sense? So don't get bogged down with like, oh, base 8, base 10. Which one takes more space? That question is not even relevant, right? So if I see you in 2 years, you're programming in C or doing a microcontroller, and you ask me, Vera, for decimal, I need more bits, right? I will just stare at you, turn around, and walk away. That question is so irrelevant, right? It's just a representation. Now, what do these things represent? It's more important. So let's do a binary. Try to convert this to decimal. What'd you get? No.
It's 79.
179?
Okay.
How'd you do it?
Added it up on 2, 16, 32, 128.
So the same way you did with the base 8, right?
No, they say no. They're small.
Well, it's arithmetic error, right? But The method is the same. What is it? 179? Okay. So it's the same thing. It's a positional number system, right? So each digit implies the magnitude of that position, right? It's just that the base of it is different. So here, like for the most significant bit, you have 1 times 2 to the 7th, which is 128. And next digit you have 64, 32, 16, etc., etc. And when you add them all together, you get the answer. Right? Any question? Straightforward? Now, do you know the significance? What's the significance of this positional number system? Something that's really convenient to us when we use our computers that are digital. It's the fact that both decimal and binary are positional number systems. What does that entail? Let's store it for a bit. Now, how do you convert from decimal to binary? How do you think you should do it? How do you work in reverse so you can get the decimal? Oh, the binary, sorry.
Divide by something.
Divide, right? So you do start doing modulos, right? So first you start with the binary magnitude that is closest but less than your number. Make sense? In this case, 928, because the next one is what? Times 2, 256. It's bigger. So you get the one where you have, where it's actually less, but the closest to it. Does that make sense? So mod, it's 1, so you have a remainder. Now you divide by the next magnitude. 64, it's less, so it's 0, etc. You get your number back. Cool? Now, what if I want to represent a number that cannot be represented by this number of bits? So now we have the concept of bit length. What do you think a bit length is?
Number of digits.
Number of digits. Why is it important? What?
Space and space.
Space, and more importantly?
You represent more than one.
Yes. The combinations of things you can represent with it. With 1 bit, how many things you can represent? 2. 2 bits? 4, 3, 8, so 2 times 2 times 2 times 2, right? So with 8, it's about 256 combinations. So with 8 bits, you can represent 256 combinations of something. It doesn't have to be a number. But if I want to represent a number, let's say I want to represent unsigned integer. What is the range of numbers I can represent with 8 bits?
Unsigned?
Unsigned.
0 to 55?
Yes. So unsigned, you go from 0 to 55. What if I want to represent 500? Is it possible with 8 bits? No. Cool? And 4 bits is wonderful. I used to have a joke slide here, but it was getting old.
It's not all that.
Okay.
Maybe we can find it.
Oh, it's everywhere. It wasn't original.
And kind of people who understand binary.
No, that's too common. Ha 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 ha. Thanks. That's why. Just dry laugh like that. So, bit length. That's why we have different types. Pair, short, int, long, 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 long. Right? So it's just how many bits represent numbers. That represent the data. Because if you declare a long and you only need to represent true or false, that's very wasteful. Don't you think? All these 4 bytes of data, just either 0 or 1. Well, come on. And then you'll see the reason why it carries the shortest data next week. So bigger data types will occupy more space. Bigger data types can represent more combinations and greater range of values. You cannot represent 1 million with 8 bits. If you may also need to represent 0 to 99999, right? You can represent 1 million with 8 bits if, for example, you're trying to represent 100,000s. Does that make sense? You get the idea here. If you want to represent unsigned integers, yes, you cannot represent 1 million with 8 bits. But if you want to represent multiples of 100,000s, there's no reason why you have to have more than bits. Does that make sense? It's all in the programmer's mind, the programmer's design. The computer is the devil. But if you want to do some arithmetic operations, make sure you are actually representing a number, because that's how computers work. Any questions so far? No? Sounds good? Now the important, yes?
Is that an orange or dragon ball? So any questions? It's been bothering me. It's more like an orange to me.
Dragon Ball has like a bright colored star.
Well, that's a little bitty star, maybe a joke.
It's an orange.
It's an orange. Somewhere I read learning is delicious. Or something like that.
There are a lot of references in my lectures, but not that many.
Oh.
It's like just the logo.
Wishful thinking, okay, which, oh.
You want more references? I can put in more references. Depends on how nerdy you guys are.
Carry on, carry on.
All right, so now, how does the implication with the CPU? Now you have a sense of things have limits. This is where our human mind differs against the computer. Our mind, when you think of big numbers, you just don't think of space, right? You say, oh, it's just a big number. You just think big. Computers, when you have big numbers and you can't represent it, what'll happen? Somebody will get fired, right? Because the answers will be wrong. Does it make sense? And somebody did get fired for that. Okay, so now I also said before that instructions are also data, right? So instructions need to be represented by combination of bits. Now for the simple CPU that we have, how many bits do we need for instructions to encode an instruction? We remember it had 4 instructions, right? So it needs at least 2 bits to have unique combinations for each instruction. Does that make sense? Now we also have 2 instructions that will load a number to a register. Here it's more variable. Depending how large a number you want to be able to load defines how long is your instruction. Does that make sense? So instruction length, we'll talk about it in the next slide. So the PLP system is 32-bit. Have you ever wondered what the 8-bit, 64-bit, 32-bit things that they market for CPUs, computers, gaming systems are? What are those? Like, what is it signifying? What length? Can you give a guess?
32 bits is 4 bytes, right?
4 bytes of what? Like you see a 64-bit CPUs. You have a 16-bit Mega Drive system back in the 90s. Like, what is it? Like, you have an 8-bit Nintendo. What width does it specify?
Floating point operations.
Kind of. So there are 2 things. First, the address bus. The second is whatever internal operations the CPU are doing. Make sense? So the width of the register or whatever. Now, what actually gets in the box is when you go to the marketing department, hey, which numbers are bigger? Oh, it has 64-bit bus and 32-bit registers. Okay, 64-bit. Right, so in the end, it's a marketing term. But it does imply something inside the computer. Now in PLP, the system is 32-bit, which means all the registers are 32 bits. And also, the buses will be 32 bits. Make sense? Now, the problem with 32 bits, if you stick with binary, it starts getting really hard to write down your numbers, right? Do you agree? Hey, give me the contents of this register. Okay, 1, 1, 1, 0, 1, 0, 0. As humans, as a pain. So that's why we have what? What base do we use to actually show the values that computers encode?
Hexadecimal.
Hexadecimal. So you have 16 unique digits. So each nibble will be grouped into one hex digit. Much easier to read. Correct? So straightforward. So you just group 4 bits together and you'll have your hexadecimal digit. Any question? No? Good. So here, basically it's the same thing. For base 16, it's a positional number system. So you get your digit and multiply it by its magnitude. F is 15, and you get your value. And if you do unsigned integer with 32 bits, you can represent up to 4,294,967,295, also known as 4 gigabyte minus 1. Any questions so far? So that's why you can only have 4 gigs of RAM on 32-bit systems, because your bus can only address that much. And we'll talk about byte addressable memory next week. So sometimes it helps to think that these are just combination of bits and not numbers, but sometimes, or many times, they are numbers that you need to do calculations on. So, but it doesn't have to be. It doesn't have to represent numbers. Cool? Now, why binary? This is where things get fun. So how do you add things? How does your mind add things? How did you just do mentally? How did you just do this calculation? I'm sure you just did. Automatically, you see 2 numbers and a plus sign. No, you calculate it, right? How did you do it? By adding what? Each digit position, right? So same thing with binary. So you have the least significant 3 bits, 0, 1, 0, 0, 1. You add them together, you get that, right? And 4th digit, you have a carry. So on and so forth, you get the answer. This is why we do binary. Because computers can do that operation really, really quickly, thanks to Boolean algebra and the math that we have. Does that make sense? Now you know why we do binary, because that's how the computer does its operations. Any questions so far? Really? Yes. What's your name?
Charles.
Charles. You're the first victim.
Yeah. So, for the off topic, what's the max order for 64-bit?
You should be able to answer the question.
I should, but hexadecimal F 8 times, so hexadecimal F.
That's the hard way to do it. As I say, with 8 bits, what's the maximum value? 256, which is 2 to the 8. Okay. With 32 bits, 232. 64 bits, number of atoms in the universe. All right?
A lot.
A lot. Will we ever see 128-bit systems? Probably not in the 100 years. I won't bet money on it, but I think 64-bit will be around for a while. Cool? Now, what if we want to represent signed numbers? So we've been talking about unsigned integer. How do computers deal with signed numbers? You know what it is?
0, 1, changing first bit to represent the sign.
No, that's not too complicated. That's sign magnitude. Sign magnitude is most significant bits of sign, right? And we will see why we don't use it. And 1's complement is when you flip all the bits to get the negative number. And 2's complement is where you flip all the bits and add 1. Turns out when you do this on a binary number, arithmetic operations will stay the same. And that's why we use 2's complement. There were computers that used sign magnitude and 1's complement back in the 60s, 70s. So with sign magnitude, I'll just skim through this because this is not really important. We just have the first bit, the most even bit we want to signify the sign. Simple intuitive for us, because that's how we deal with sign numbers. That's how we represent sign numbers. But the computers will be complex. And you'll have 2 representations for zeros, which is useless. Now 1's complement, same thing, you have 2 representations, but the logic will be better if you implement it in a computer. 2's complement, it works. I have no idea who came up with it. There was some Boolean algebra expert. But the way you do it, let's say you want to represent -50. The way you do it, you take number 50 in binary, flip all the bits, add 1, boom, you get -50. So for sign integers, you have only 1 0 representation. That's good. So now you can represent from -128 to 127. The thing that is crazy is like LUs, you know what LUs are from last Monday, right? That are designed to work with unsigned integer will work with 2's complement. No change. Believe me? Want to see it in action? Because now you know binary, right? So, show me. Do these. You have 2 minutes. First part is pretty simple enough, right? I'm more interested in how you do the 2's complement. Done? Charles? Is everybody done with the first part of this? So how's the unsigned one, the first part? Easy? So it's just like in the slides before, right? You just add the each position, and you get your answer. That make sense? So you have for this one, you just add each digit, right? Now, what about the two's complement? Now, let's do the two's complement before we finish for tonight. Turn off. So for the two's complements, what was it? Negative 79 plus what?
32 plus 32.
So in decimal, what is the answer? Minus what?
37.
Right? Unless you have a computer, I guess.
No, 47.
47. This room is under equipped. So 32 is simple. What's 32 in binary? 0, 0, 5 zeros and a 1. What? 32? Now 79 is a negative number. So first we did the positive of 79. What is it? So 79 is 0, 1, 1. Are you sure? No.
0, 0.
Right. 64 plus
It should
16.
be 2, 0. It should be 0, 1, 0, 0.
Yes.
1, 1, 1, 1.
0, 1, 0, 0, 1.
And then 4 ones.
Is that right?
1, 0, 0.
64 plus 15. Yes, that's right. So to make negative, you flip out everything and you add 1, right? So this is negative 79 in 2's complement. Let's see how this works. So you have 1, 0, 1, 1, 0, 0, 0, 1. Now I said before, the LU should just work, which means I should be able to just add these two numbers and get my answer. Right? Should we do it? I hope this works. So 1, 0, 0, 0, 1, 0, 1, 1, right? Now let's check if this is negative 47. Now what's 47 in binary? 0, 0, 1.
0,
0.
1.
So 32, 40 plus 7, right? Right? Now, if you want to get negative 47, we flip all the bits and add 1. What do we see? Did we get the right answer? Yes, we did. So negative 47, there. So in 2's complement, you don't have to change anything in the CPU. You just, when you program, you say this is a 2's complement. When you do the addition, you should get the correct answer. Unless, we'll see next week. Can anybody guess what could give you the wrong answer? If what?
The number's too large.
Number is too large, which is called the overflow. So we'll talk about overflow tomorrow, probably in the lab, or next week. You guys should, so everybody should be the same lab, right? 2, 3, 15. So you will meet your TA for the first time. And have a good night.